In this lesson, we're going to be learning all about the arrangement of the periodic table and how to read important information off of the table, as this will help you in all of your chemistry career. The first thing we want to know about the periodic table is some terminology. The periodic table is arranged into rows that are called periods. So, for example, sodium's row, starting with Na here, the third row down is period 3. The columns are referred to as either groups or families, and we will see why these terms periods and families come about a little bit later on. All the different color coordinating on the periodic table, and each periodic table has its own color schemes, but you'll see that there's a pattern to how they're laid out. All have to do with what grouping the elements into different by their properties. And that's really what the periodic table is about, is grouping the elements by their properties. And we'll get more into this as we go. I want to point out how we read the individual boxes on the periodic table, because this is a very important skill. The first thing I want to point out is the symbol itself. The element symbol always has the first letter as a capital letter and the second as a lowercase letter. I purposely picked chlorine because this is a common one where people think this says Ci, but if it was Ci, this second letter would be a lowercase I, and so you would very clearly be able to see that it was an I, since it would have a dot on it for a lowercase I. And this can't be this can't be an I, because then it would be an uppercase I. The second letter is always lowercase. So that's the element symbol. It's always going to be either one or two letters. And then we have the element name spelled out on there. Now, the periodic table is not designed to look up the names for the symbols. If it was, it'd be arranged alphabetically, which obviously, if you look around, it is not. The other important information that's on the periodic table is the atomic number, which we've already dealt with, and that is the number of protons the element has, which is unique to each element. So chlorine is atomic number 17. And then the atomic mass, which is the average mass of all the isotopes of chlorine. You may wonder why some of the symbols match up with some of the names the way they do. Chlorine is obvious, Cl, chlorine makes sense. But a lot of them don't, and that's because they had other Latin names before English, came around, okay, or at least got into the scientific world. When we look at the periodic table, we can think of the periodic table as being arranged into a few different groups. First, there's one way of grouping the periodic table that just puts it into three big groups. There's the metals in blue, which pretty much occupies all of the left-hand side of the periodic table. The nonmetals that are shaded here in pink, which pretty much occupies the right-hand side of the periodic table. And then the semi-metals, or the metalloids, making this stair step down the border between the metals and the nonmetals. The periodic table can also consist of many smaller groups. The ones that you'll be responsible for knowing are the alkali metals, the alkaline metals, the transition metals, the intertransition metals, the halogens, and the noble gases. Each one of these has some characteristic properties that you'll be learning about, where that sets them apart from other metals or other elements on the periodic table. For example, the halogens are all diatomic gases. They're mostly brightly colored. The noble gases are all unreactive. The transition metals, it's really hard to tell one transition metal apart from the others. They're very similar. And the intertransition metals, even more so, where if you have a mixture of different intertransition metals all together, and generally they are found mixed together, it's very hard to separate them out. A little bit more about metals. Metals, we all have seen before, have that characteristic metallic luster. They're very good conductors of heat and electricity, and they are malleable, which means they're easy to bend and shape into different shapes by like pounding them, say, with a hammer. Non-metals, on the other hand, which this red powder would be a good example of a non-metal. This is phosphorus, red phosphorus, are dull, they're poor conductors, and they're very brittle. So if you hit them with a hammer, you're not going to be able to shape them into a tool. They'll just break into dust. And then semi-metals have some properties of each. So you can see in the middle here, the silicon. Silicon is very shiny, like a metal. It's very brittle, like a non-metal. It's not a great conductor, but it's an okay conductor. In fact, silicon would be considered a semiconductor. Let's look next. Why is the periodic table called the periodic table? What does it mean by periodic, and why does it have the funny shape? It's called the periodic table because properties, as you go around the table, you'll see that they repeat. So let's look at an example. As we go across the table, so starting with lithium, lithium reacts with water. Beryllium also reacts with water. As I go a little bit on, I don't really know anything special about boron. Carbon, I don't have anything under here that goes with that. But I finally get to oxygen. Now oxygen, you wouldn't think of being smelly, we're around it all the time, but ozone is very smelly, and that's made out of oxygen. Fluorine forms a poisonous gas. Neon is a very unreactive gas, and so is helium above that. Continuing down to the next row, sodium reacts with water. Magnesium reacts with water. Sulfur is very smelly. Chlorine is a poisonous gas. And argon is a very unreactive gas. Going down to the next row, potassium and calcium both, guess what, react with water. Selenium is very smelly. Bromine makes a poisonous gas. And I forgot, copper is an unreactive metal. And then krypton is a very unreactive gas. I can keep filling this out and we're going to get the same exact pattern filling in as I go because this pattern has a certain period that it repeats over. Now the period that the patterns in the periodic table repeat over, it doesn't take the same number of elements each time. The first time the pattern repeats, it actually only takes 2 elements. The next time it takes 8, and then 8 again, then 18, then 18 again. Then after that it's actually 34, adding because these 2 rows slide up. So that's where this term periodic comes in, is the repeating patterns that are found in the periodic table, and we'll talk more about these patterns as we go. The underlying cause of these patterns is really the electron configuration, what the electrons are doing. When we look at the first group of the periodic table, those alkali metals, we'll find that if you look at the outside energy level, they have just 1 electron in it. 1 electron that is very free to go. So in lithium, sodium, potassium, all of them just have this 1 electron, and I'm just going to highlight this 1 electron that all of them have in this outside level. If we look in the second column, all elements in the second column have 2 electrons that are ready to go. So they all have similar behaviors. As I look in the 7th column, each one is just 1 electron short of a full level. So the full level generally consists of 8 electrons. And so we are just 1 electron short as fluorine of being a full level. 1 electron short in chlorine. 1 electron short in bromine of being full. Whereas the noble gases on the very end of the periodic table have full levels. They have 8 electrons in that outside level, and they're happy having those 8 electrons. And so that makes them very unreactive. So again, the underlying cause of this repeating pattern in the periodic table is a repeating pattern in how electrons are filling up the energy levels of the atom. So those spaces outside the nucleus. One of the trends in the periodic table that I want you to understand is the trend in atomic radius. As you look at the atomic radii of different atoms, so these are atoms kind of drawn to scale, you'll notice that pretty much without exception, as you go down the periodic table, the atoms get bigger. And that's as they add more energy levels, they get larger. As you go across the periodic table, the atoms tend to get smaller. There's maybe a few exceptions there, but overall the atoms get smaller. Now you'd think that they would get bigger as they're getting more things in that atoms, but as you go to the right, the pull of the nucleus gets stronger and pulls those energy levels in tighter, so they get much smaller. You can see like there's other trends like in density. Now this isn't as nice of a trend. It kind of goes up and down and up and down. But the fact is it goes up and down like across every single period. So it goes up then down, and it does that over and over and over again in a very periodic pattern. It's not like a perfect match of a pattern, but there is somewhat of a pattern to it. We can use these repeating patterns of the periodic table to predict unknown properties. For example, if we have already measured the fact that iron has a melting point of 1811 Kelvin and nickel has a melting point of 1728 Kelvin, we can estimate the melting point of cobalt. Cobalt falls in between iron and nickel on the periodic table, and so because of these periodic patterns that form on the table, we should expect that it probably has a melting point somewhere in between those two. It's not perfect, it's not a perfect system, it's not infallible, but it's possible. So if we take the average of 1811 and 1728, we get 1770 Kelvin as an average. If we look at the periodic table to find what the actual value is for the melting point of cobalt, we find that it's 1768. So just by averaging out these two values, you're only getting off by 2 Kelvin, which is really a very small error indeed. Now, this isn't, like I said, going to work out perfectly for everything. If I did the same thing with the density of iron and the density of nickel to try to find the density of cobalt, um, I actually started off with the example being that, and you will be way off because the density of cobalt is actually very close to the density of, um, of nickel. And so again, when you go back and look at these things, if you're in one of these linear regions and you're trying to estimate the properties of something in the middle, it's going to work out really well. But if you're choosing, for example, something that's on one side of a peak and another side of the peak and trying to estimate the value of something, you're going to be wrong because you didn't realize that it peaked there in the middle. So again, sometimes if you're in a linear portion, you're going to be able to estimate a property very well. Based on doing an average. However, sometimes, depending on what's happening with the trend, you might be very far off. Okay? So hopefully this will help you get through your homework on the periodic table.